So you got the Alex thing pushed back to like uh,
December.
December. Got it. When do you start classes? Your fall semester.
I start next Wednesday.
Oh, okay, that's pretty soon. So what do you want to work on today?
Uh, we just keep doing what we're doing, I guess.
Alex stuff.
Yeah.
What are you taking? What are you taking in the fall?
I'm taking a political science course, two history courses, and then um my intro to cell bio course.
Got it.
That's the science.
When are you taking Orgo?
It'll have to be next semester.
Got it.
Yeah. My surgery pushed back everything
Mm-hmm.
and stuff. I was supposed to.
All right. Molecules of four imaginary substances are sketched. Table below. Decreasing order of strength of intermolecular forces in them. Um. Okay. All right. I guess. Yeah. So like, blue is the positive dipole. Red is the negative one. And then
Yeah.
for the ones that are just white, I guess they're completely nonpolar. So let's see. Bigger molecules will experience the stronger dispersion forces. Okay. Dipole forces for if they have dipoles. When partial charges cancel out through symmetry. Okay. Alright, let's see. So, okay, D just has that one negative pole. And, oh, there's like some blue, I guess, on the ones on the side. Or maybe I'm. No, I'm just seeing that. Never mind.
No.
Okay, so that's the highest. Let's see. Followed by the one that has these two positive charges, two negative charges. Okay. And then between B and C, I guess that's where just the size comes into play. Because they don't have any dipole moments. So they're saying, like, if two molecules both have dipole moments, compare the size of the moments.
Yes.
Okay. So, like, A and D are the same sizes. Okay.
All right.
Okay. Yeah, we could try it.
Yeah. Well, there you go.
Okay, so um okay, I think C will be number 1 because it's the biggest molecule and it also has like a dipole moment. Oh, I said C.
We'll see. Yes.
I think that'll be the highest. Then A and B both are the same size, but A has It seems like a positive in the middle, negative, negative. Maybe that's 2. I don't know if like they cancel out or anything. Let's see. And then that one, B, I think would be 3, and then D is 4. So I'm not sure about this because I'm still trying to see if like A, the dipole moments cancel out or not. Okay, damn. Alright, maybe A and B you can switch.
Yep.
Okay, so apparently, alright, so like A, I think they cancel each other out.
Yep.
Okay, now here, so I think A will be number 1.
Number 1?
Yeah, because it's just a negative in one direction, and then C, I think, will be number 2.
Okay.
It's the same size as A, but I think those negative dipoles or poles just cancel. Well, they don't completely cancel each other out, but they're all pulling in opposite directions, so maybe that would be... Okay. Yeah.
Check it. Should I check it?
Yeah. Cool. Alright, so this one, B is going to be number 1. Wait, hold on. I'm trying to see if these cancel out or not. Like, okay. So, let me see. I'm trying to think, like, if the negatives cancel or the positive and negative cancel. So, if the positive and negative cancels out... Okay, so I think C will be number 1.
Okay.
And then I think B will be number 2. Then A is 3 and D is 4. This one might be wrong though.
We'll see.
Yeah. Damn.
Yeah.
So switch B and C. Yeah.
Yeah. Okay, so it seems... I guess it wants to see that if they're more balanced out rather than, I guess, like this.
Yeah, so I thought
Because you see it's more faded in the middle here, but then all of them have red.
yeah,
Which means
so
that the intermolecular force may not be really strong because it's overpowered by one side.
yeah, I think I was thinking first like a positive is gonna cancel out the negative, but I think the negatives cancel each other out and the positives cancel each other out. It's like it's
Yeah.
different from... Alright, so this one, so okay, this one will be C first, and then D, and then A, and then B. Wait,
Oh, whoops. Sorry.
yeah. Mm-hmm.
Right.
For each compound in the table below, decide whether there would be any hydrogen bonding force between molecules of the compound or between molecules of the compound and molecules of water. Okay. So we're looking for, like, fawn. So between molecules, I think. Okay. I don't know
Oh, quickly,
if any of. Yeah.
if you're recording, you can. If you want to record, you can.
Okay.
I know I told you that you can, but all the time, but
Okay.
just in case.
Yep.
Just in case you forgot.
Mm-hmm. Yeah. So okay, let's see the answer. It seems like none of those have fawn in it. So I don't. Okay, let's see. Oh, sorry. The one in the middle has fawn in it. So basically, like,
Fawn stands for what again?
oh, it just F. It's just fluorine,
Oh, fluorine,
oxygen, and
oxygen,
nitrogen.
and nickel, and nitrogen, yes.
Mm-hmm. Yeah. So it's going to. So let's see. No, 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 no. Okay.
Oh, okay, so this is pretty straightforward.
Yeah. Okay, so that one
So
has
this one,
an N in it.
yeah.
So between, yeah, it'll be yes to both, I believe.
Yes.
And now this one has fluorine in it. Well, okay. I know for acetic acid it's going to be yes for both of them.
This one?
Mm-hmm. Now, I think
This one should be yes for this, probably no for the next, right?
I think the F has to be, let's see, difluoromethane. I'm trying to think. Because I think it's going to be no. Because the fluorine has, like, the fawn has to be bound to hydrogens. So this one, difluoromethane, it's just, like, it's the fluorine is bound to the carbon.
Oh, okay, I see.
And, yeah, there's that. I think between, yeah, you still have one left. I think that one's going to be no. Damn it.
So it should be yes, yes then?
Let's see.
I was the first one, nothing can hurt.
Okay.
It was yes, no, then. It was no and then yes.
Okay, so
Between
it
the
can
molecules
bound
of the
to...
compound
Okay.
and of the water. Oh, okay. Alright. Well, now we know. NH3 should be yes, yes, right?
I think so, yeah. This one will be no, yes. Wait. Sorry. It doesn't have font, so it's no. Oh yeah, this is like before, so yes. Okay. That's gonna be yes. This, well, the oxygen isn't bound to any hydrogen, so it'll be no. And I think that'll be
Yes, I think.
Yeah, maybe. I mean, ether is like a nonpolar solvent, which means that it shouldn't. But I'm not really sure. Yeah, that one's gonna be no. Alright, let's check. Alright, nice.
Yeah.
Okay. 250 topics left.
Yep.
That is crazy. Alright, rank this in decreasing order of their boiling points.
CH4 is methane.
So the more, the bigger it is, the larger the boiling point, and the stronger the whatever. Wait, what is that? The bonding forces.
Where are you reading?
Oh, just the explanation. Strong bonding forces in the liquid state. NbCl. Okay. And then intermolecular forces. Alright, let's see what they put as the answer. I'm gonna like screenshot like the answer to use as a reference. So, okay, so...
Oh, because they're also
Yep.
using the, what do you call it? The grams.
Mm-hmm.
Like how much it weighs would be the higher the boiling point.
Yeah.
So, okay.
Can
So
you
it
scroll up? I
seems...
just want to see what their explanation is for number one. Like, where they said, okay, strong binding forces, okay, most important are metal elements and binary ionic compounds. The very strong bonding forces holding these substances together in the liquid state gives them very high. Okay, so niobium. I never even heard of that. Niobium chloride is a binary ionic compound. The very strong ionic forces between niobium ions and chloride ions in the liquid state will give this the highest boiling point. Binary ionic compounds apparently are number one.
Okay. Binary ionic. Okay. Well, ionic because it's metal and a non-metal.
Yeah.
And then... Oh, God. Okay, so it's just two elements.
Yeah.
Okay, so I guess metal elements and binary ionic compounds. Oh, okay. All right then. Right?
Yeah. Let's see.
H2. Let's see what's higher.
Hg. Yeah,
is,
that might be the highest because that's like a binary ionic compound.
Yeah.
So
That's mercury and chlorine. Yeah. I think that'll probably be the highest.
Yeah.
Next highest. Well, what's the grams per mole chloride? Chlorine is it 35? Is that the molecular mass?
I forgot. Let me see.
I got a periodic table.
Yep.
Yes,
Good job.
35.45. Sorry, I got a new monitor, so I'm still trying to figure out some stuff.
Oh, nice. What type of monitor?
It's 32-inch. It's a Samsung Smart Tizen 4K.
Mm-hmm.
So.
I showed you mine, right? This is like...
See. Oh, you got a curved one. Yeah, you got like an ultra-wide thing.
A curved one, and then I have this one that
I
can
that
rotate. And that one also. It's hard to see.
Yeah, that's crazy. It's a lot. How big is the ultra-wide one? Is it like 49-inch? Is it 42 or something?
I'm not sure. Let me see. It is 35 inches. It's like 4K also, and it has 100 or 120 hertz refresh rate
With 60 frames per second.
Oh, like 120?
Oh, it's 120 frames per second. Wow. Okay.
Yeah, I got it like on sale from like Slick Deals or something.
Oh, wow, that's pretty good.
Yep.
How much was it? This one was like 310, 315. I actually got it on sale. This
300.
one off like 75. Nice.
300.
Yeah, this one has USB-C as well, and that's why I needed it
Mm-hmm.
because I have the Mac.
Yeah, I don't know if I ever showed you my computer, but that's it over there.
Oh yeah, you only told me about it, or told show me that.
Yeah. And like
You put that all on your own.
these are like the hard drives on it.
Mm-hmm.
I'm always defragging. Okay.
How's the new place? You live by yourself there?
Yep. It's pretty good. My room gets a lot of light. Like, there's that window over there. Then there's like a really big window over here. It's like a whiteboard.
Oh, that's awesome.
Yep.
All right.
I mean, I'm gonna.
Well, this has
have
to
a
be the
feeling that's
lowest.
gonna be the lowest. Yeah. And then
Oxygen
that's
is 16, 16 is 32.
34.
So this one's actually going to be the highest. I mean, this one's going to be the next highest, sorry.
Well, so when they're similar, when they're similar weights, I think you consider like the polarity or something.
Oh,
And
wait, okay.
I think HCl has more is more polar, and
Okay.
B is less polar. So I think HCl might be wait. Yeah, I forgot what they said when the molecular weights are similar. But I think HCl is going to be 2, and B is going to be 3.
Oh, the way I had it before. Okay.
Yeah, I could be completely wrong though. Damn it.
Alright, so then we gotta switch it. Because then maybe because it's bigger. Yeah. Okay. Makes sense. Oh, Jesus. Okay.
So that one and D. So okay, argon's gonna be the lowest.
Gas.
Yeah, and then Cr. I think that's like a transition metal or something.
That should be.
It's not chromium, is it?
I think it is chromium.
Yeah, chromium.
Because I know cesium should be Cs, right?
Yeah, it's chromium.
Yeah, it is chromium. Okay. Wait, where's chromium again on this?
It's next to it's 24.
There it is. Yeah, it's 24. Got it. I knew manganese was near. Okay. So chromium.
I think that'll be the highest. It's just straight up a metal.
Yeah, it's a straight up transition metal.
Okay, now between A and D, let's see. Well, okay, so we have 3 carbons and an oxygen here. We have 2 carbons and a nitrogen. A is going to be heavier. So that could be a 2, and D could be a 3. Nice. So you hooked up your laptop to your monitor like that?
Yeah.
And you can display it at like 4K, like 38, or what is it, like 38 something? The resolution.
Yeah, it should be 60.
Wait, you're not the refresh rate, like the resolution.
Oh yeah. Yeah, it should be like 38 something.
Yeah.
It displays it in straight up 4K.
Yeah, this monitor Since it's curved, it's like a weird ratio, but it's 3440 by 1440. But my other monitor that is on the side over here, that's like true 4K, and it can go up to 4096 by 2160.
Oh, wow. Yeah, that's how my TV goes.
Mm-hmm.
Up to. I don't know about this one.
Alright, let's see. This one over here. I have a feeling that F2 gas is going to be like the lowest. Okay, now we have like a carboxylic acid. We have. Okay, so okay, D might be this. Wait. Okay, so we have a carbonyl and a fluorine for A. And for C, we have a carboxylic acid. Fluorine weighs more than oxygen. So A could be number 1 and C could be number 2. But it might be C and D. Yeah, okay, damn. So try C as number 1 and A is number 2. Because there's like the hydrogen bonding stuff.
Yeah.
Okay.
Mm-hmm.
Okay, Fe is going to be the highest, so it'll be 1. Because it's just iron. Oh, Fe.
Wait, whoops.
Helium will be the lowest. Okay, now it's going to be... Okay, so... I think D, that's HCN. That's actually like cyanide right there. Yeah, because it has a nitrogen, which weighs more than a carbon, and it's like very polar. So I think D could be number... Wait, D could be number 2.
Okay.
And A could be whatever is left. What, like number 3? But I could be wrong about A and D. I still haven't been able to figure that part out.
I mean, if it goes into weight, this weighs more.
Yes, but they said like when they're close
However,
when they're close in weight, there's like another like
I
there's
think
a
this
third
might play the difference.
third thing to look at. Like all I can
this
notice is
one's more...
that A is non-polar and D is polar. And in the last question, I thought that the polar one... Wait. No, that was because of a different reason. Anyway, I'll get my answer whether or not polar means it's going to be a higher boiling point or not. I guess when you check this one.
Okay. Yeah.
All right. Okay. So everything has dispersion forces, so that's going to be the thing all the time. Dipole is only for polar, and hydrogen bonding is the FON stuff. So dispersion will be all of them. A dipole will be water. It'll be chloromethane. Hydrogen bonding will be water only.
Carbon monoxide, no? That's fun.
No, because for FON you need that like
a hydrogen.
Yeah, like the fluorine or the oxygen or the nitrogen has to be bound to a hydrogen. So
Yeah. Okay.
wait. Carbon monoxide dipole. Oh, yeah. Sorry. Carbon monoxide is just a carbon triple bonded to an oxygen, and the oxygen is electronegative, so there's a dipole there. I was thinking of carbon dioxide, which which doesn't have the dipole. But okay, I think I could do this. So yeah, everything's gonna be dispersion. Dipole should be hydrobromous acid. Wait. What the hell? Yeah, I think so. Yeah. Alright, and then hydrogen bonding.
Let's read it.
Hydrogen. Oh, yeah. That should be. Wait. So the fluoromethane, I don't think that's going to be hydrogen bonding. Yeah, I don't know if that's going to be, because I think the F has to be
bound.
Yeah, I think the F has to be bound to an H.
Okay. I want to try it like this.
I mean, I can look it up. Let me see. Hydrogen bonding fawn. Hydrogen bonding occurs only between molecules with lone pairs on center atom and hydrogen bonded to F, O, or N. So yeah, basically you need the thing to be bound to a hydrogen.
Okay.
So like HF is an example. Damn it. Oh wait. Fluoromethane has a dipole.
And carbonyl sulfide? Dipole as well because it doesn't have a hydrogen bond.
Let's see. Carbonyl sulfide. That's a C double bonded to an O, and then bonded to an S. Let's see. Carbonyl sulfide. Oh, wait. So it's...
Thank you.
Wait, what's up?
No, nothing else.
Okay. Yeah, no. Okay, so that's basically like CO2, except one of the oxygens is replaced with a sulfur. And sulfur is more electronegative, right? From the here, show me that periodic table. Sulfur, where is that? Okay, yeah, it's 2 to the right, 1 down. I think it's more electronegative, right?
Yeah. What the hell's going on?
Oh, cool. There's a lot of stuff you can do there. Where it says electronegativity or whatever. Electronegativity. Oh, it says it gives you values. So, like here, go to sulfur. Okay, 2.58. Go to. Oh wait, I'm comparing it to oxygen. It's actually less electronegative than oxygen. Oxygen is. Go up to oxygen. 3.44, yeah. So oxygen is going to pull more. So it's going to have a dipole.
Yeah, I was figuring it would just because it doesn't have, it's saying it's wrong and it doesn't have any hydrogen.
Mm-hmm. Yeah.
Ammonia, NH3.
So ammonia is going to have all three.
Yes.
Carbon tetrachloride, hydrogen chloride is going to be dipole as well. Yeah, that should. Oh, that's not gonna. Yeah, that's not gonna. Yeah.
That should be the answer, right?
Yeah.
Mm,
Hydrogen fluoride is going to
fluoride.
have all three.
Fluorine.
Okay.
Nothing.
Difluoromethane is going to have a dipole. Let's see, nitrogen trichloride. So that means it's nitrogen bound to 3 different chloride. So that's going to have a dipole. All right. Dispersion, all ion dipole. Ions and polar molecules exert an ion dipole on each other. Okay. So dispersion will be everything. Dipole, okay. Okay. All right, CH2, CCl2. Okay, so that's like, okay, dichloroethylene. At the ethylene part means it's like a double bond. Here, let me get my notebook. I'm just gonna draw these. So this guy is a C. I have to get another pen. Let's see. Whatever. I'll just use this pen. So we got a C with 2 H's on it, bound to another C with 2 Cl's on it. Okay, so yeah, alright, good. Dispersion. There's gonna be ethylene. Oh yeah, that's a double bond. 1, 2, 3, 4. Okay. So yeah, there's going to be a dipole also. And yeah, that should be it. Damn it. But also one extra name. Wait, what? Correct forces, but also one extra name. What do they mean by name?
Ion dipole.
No, there's no ions here.
Wait, also one extra name?
They said that we have one extra name, so maybe the dipole one isn't there.
It contains the correct forces, though.
Dichloroethylene, let me see.
So maybe just dipole. Get rid of dispersion.
There are different ways of writing dichloroethylene.
Oh.
There's like...
It was ion dipole.
Oh, she is. Okay, ions and polar molecules exert what? Okay, let's see. Where did the freaking K plus thing come from?
Oh, it did say potassium cation.
Damn it.
Damn it. Yeah.
Okay.
Whoops.
But wait, okay. So, okay. Okay, two argon atoms. I mean, that's just going to be dispersion.
Yeah. Shouldn't be anything else. It's in a water molecule and chloramine.
Okay. So this is going to
Hydrogen.
have wait. No, yeah, hydrogen bonding. And dipole, just regular dipole.
Let's try it. Yes.
Yeah. Hydrogen bromide and dichlorine monoxide molecule. Dichlorine monoxide. What the? So that's C. Double bonded to an O, and then bonded to two Cl groups.
Bromine is a metal, no? No, non-metal.
What's that? Yeah, it's a non-metal. But hydrogen
So
bromide.
there should be no dion dipole.
Hydrogen yeah, what's up? So there could be a hydrogen bonding here, and then a dipole. I wonder if the hydrogen bromide, because it's an acid, if that'll. Well, I guess they'll tell you like an ion or whatever.
Yeah.
Okay. Damn it.
Ion dipole. Oh, damn it.
Okay. Yeah, I was thinking about that because HBr turns into H plus and Br minus because it's an acid. So I don't know if they wanted, us to think of that, but I guess they do.
What?
Oh no! Why do they take like more points off? All right, what did we do here? Dipole. Damn it! So neither the HBr nor the Cl2O. Oh my God! Wait. I know what I did wrong. I thought that there's a carbon in the dichlorine monoxide.
Shit.
So it's really just an oxygen bound to two chlorines.
Bromide, anion, and ammonia molecule. So dispersion and ion dipole, I think.
Yeah.
I'm wrong. Okay.
Helium atom and acetylene.
Acetylene, yeah. Well, started as that, but CH2.
Yeah, so the acetylene doesn't have any dipole. And helium atom, I mean, that, is just like a gas, isn't it?
Yeah. Would there be any hydrogen bonding?
No. There's no FON.
So then it should just be dispersion, no?
Yeah, I hope so. Okay, cool.
Hydrogen peroxide, so it's H&O, that's already hydrogen bonding. Then hydrogen fluoride. So yeah, that's most definitely hydrogen bonding. bonding. Is there a dipole working here?
Hydrogen peroxide, I think doesn't have. Wait. So for that last one, wait, hold on. Let's see. If there's an ion kind of thing going on. So let me think about that previous. Wait, the ion thing wasn't in the previous one, so I don't think it'll be in this one.
So it should just be dipole?
Let's see.
Or no
Hydrogen
dipole?
peroxide doesn't have a dipole, but hydrogen fluoride
Fluoride
does.
does.
So
Yeah, so it says all at work. So
okay.
should be.
All right. Good call. I'm gonna use the bathroom real quick.
Ah, damn it. Back to this bullshit.
Okay. Liquid X is known to have a higher viscosity and higher surface tension than liquid Y. Use these facts to predict the results of each experiment. Here, why don't you scroll down so I could see the explanation and the answer, and I'm going to take a screenshot. Okay. Alright, so this is basically saying, let's see, identical wire loops are, so okay. Viscosity, resistance to flow. Surface tension, resistance to penetration of a surface. So fluids that form more compact, round, or drops on surfaces. Okay, vapor pressure. Liquids with high vapor pressure evaporate quickly when in a closed container. Produce higher partial pressure. Okay. So identical wire loops are dipped into liquid X and liquid Y so that a film of liquid forms across the loops like a bubble solution. Okay. The width of each loop is increased slowly, and the forces Fx and Fy needed to make the loops 5% wider are measured. So which force will be greater? So wait. Force resisting the expansion of the loop is surface tension. Since expanding the loop increases the surface area of the thin film of liquid. Okay. Liquid X had the higher surface tension. Higher viscosity, more pressure to push it through a tube. Okay. let me see the top again. Okay, liquid X. Oh, it has higher surface tension also. Okay, so let's see. So viscosity is inversely proportional to whatever, whatever flow, and then surface tension is proportional to let's see. Is proportional to wait. Force resisting the expansion. Oh, compact. So surface tension is proportional to is inversely proportional to the size of the droplets. Okay.
Starting.
Then vapor pressure is proportional to partial pressure. Okay. Okay, let's go for it. All right. So liquid X. Okay, so higher. Okay. So beaker of liquid X submerged in large. Wait, a beaker is submerged in a large container of liquid X turned upside down, and another beaker submerged and turned upside down in a large container of liquid Y. Hydrogen gas is bubbled into each upside down beaker until 100 ml of liquid has been displaced. The masses for X and Y of hydrogen inside each beaker is then chemically determined. Note, for advanced students, you may assume the solubility of H2 in either liquid is very low. So that means that it's not going to be inside of the liquid as much. Okay, so higher vapor pressure means that there's going to be a higher partial pressure of the liquid higher partial pressure of the gas. So now how does that relate to the masses? Higher partial pressure means that it's going to give off. Wait, oh yeah, I screenshotted this. So vapor pressure, how quickly and completely liquid evaporates. Liquids with a high vapor pressure evaporate quickly, and when in a closed container, produce a higher partial pressure of vapor at equilibrium. Okay, so if it evaporates, the masses are of the hydrogen inside each beaker. What? Okay, I don't know how to do that one. Let me look at the second row. 25 ml of liquid X are put in one sealed 5-liter flask. Same thing with liquid Y. The pressure in each flask is then slowly lowered with a vacuum pump. Okay, so the pressure in each flask is slowly lowered. So the thing with a higher vapor pressure in a closed container produces a higher partial pressure. Okay, so liquid X has a higher partial pressure in a closed container. Now, what does that mean? That means that boiling is when the partial pressure is equal to the atmospheric pressure. So I'm going to guess the pressure in each flask is slowly lowered with a vacuum pump. So okay, like first my guess would be X first, then Y, but I'm trying to connect how a vacuum pump affects the thing, because it's like in vacuum filtration, so here, let's see. Vacuum filtration reason. Vacuum filtration, like, I think it lowers some type of pressure thing. Vacuum filtration. Why do we use vacuum filtration? Okay, can be used under high pressures. I think so. Yeah, I remember. So I think it does something like it lowers the pressure, which means that it should lower. So okay, wait. If the pressure in each flask is lowered, and you need it to be, I don't know if this is in my notes or not. Okay. Got it. So vacuum filtration causes the atmospheric pressure to decrease, which means the vapor pressure decreases and the boiling point decreases. So the boiling point, okay, so the vapor pressure decreases, and vacuum filtration is used for things that have really high boiling points. Okay, so the boiling point is decreased. Okay, I mean, I'm gonna go still with eventually both liquids boil, X first, and then Y. Yeah, and then, let's see, for this one, the masses of hydrogen inside each beaker. Damn. So, higher vapor pressure. higher vapor pressure. Vapor pressure. So, okay, maybe the surface area comes into play here.
Okay.
That means that it resists penetration. Now, when they bubble the hydrogen gas, until it still says until 100 ml of liquid has been displaced, the masses of the hydrogen gas, the volume between the two is the same. The masses should be the same too. I don't know. I don't know if it is. So they're saying the solubility in either liquid is very low. So it's just going. Yeah, what the hell? Alright, I mean, either they're going to be equal or impossible to predict. Honestly, don't know at all.
Let's try the impossible.
Let's try an equal. All right.
No.
Damn, yo. So it will be less. So I wonder if that's due to surface tension. Let's see. In the first row, higher vapor pressure means the equilibrium partial pressure of X vapor above the liquid will be higher. That means that there will be more X vapor and less H2. Okay, I think I see. So I thought that the 100 ml of liquid that's been displaced is caused by the H2 gas. But it just says that hydrogen gas is bubbled in until 100 mLs of the liquid has been displaced. So it doesn't mean that all 100 mLs of that is the H2 gas. So basically for liquid X, that 100 ml of collected gases includes liquid X vapor and H2O. So okay, I'm going to take another screenshot of this. Here, I'll save this. Or I'll just write it here. So basically, And then let me just see the explanation for the second row. Second row, liquids boil when applied pressure equals a vapor pressure. The liquids are not initially boiling. Pressure must start off higher, but since pressure is then lower, it'll eventually fall below both vapor pressures, so they'll both eventually boil. Okay, let's try the next one. Okay, so A, lower surface tension and lower viscosity. So we're just going to consider B to be higher. Okay, so B has a higher viscosity, so the time for B is going to be time A is less than time B. And then this one, A and B are both mixed together. They're mixed together.
Can't even tell anything there.
Let's see. Because surface tension means resistance to penetration. So, oh wait, they're saying layers on top of. Okay, so A is easier to penetrate, like the surface of, than B. So I'm gonna guess A will form a layer on top of B. Yeah, that's my guess.
A will form a layer on top of B?
Yeah, it could be a homogeneous mixture, but let's see. Damn it.
Homogeneous?
Yeah, why not?
No, it's probably going to be impossible. Yeah, that's what I was thinking.
Damn it. Okay. Let's see. Wait, so... Oh, I was going to look at that.
Oh, shit. My fault.
It's
Sorry.
okay.
Sorry.
We can figure it out. So let's see. A, higher vapor pressure, higher surface tension, okay? Small amounts of A and B are sprayed in the air, form perfect spheres with a volume of the diameters. Okay, so surface area, so surface tension, it means it's going to be smaller droplets. So the surface area of A is less than surface area of B. All right, and then, okay, this is just, wait. Poured in a beaker, poured into another beaker, 90 minutes. The volumes of liquid in each beaker are measured.
Impossible.
So higher vapor pressure, though, means that more of it will go into the vapor phase, so less of it will exist as a liquid. So volume of A will be less than volume of B. I'm pretty certain about that. Let's see what we get. Damn. Okay, at least the second one was right. What's the correct answer? They're equal. All right, what does the explanation say for this? Why are they equal? It doesn't even really explain it.
Damn, it's saying work on something else.
Let's try it again, like one more time. You want to try it one more time, or you're like after this?
Wasn't letting me do something really quick.
Okay, sure.
Okay.
High vapor pressure, higher. Okay. 2 flasks are evacuated and sealed. Into one flask, into the other flask. 30. The pressures are okay. They're sealed, so the gases aren't leaving. The pressures are okay. Partial pressure. So vapor pressure is proportional to the partial pressure. So px should be greater than py. Pretty certain about that. Now let's see. This sprayed into the aircraft. So, last time it said that they were equal. Surface
Well, they do have the
tension.
same volume. So
Fluids
it's very
that
well
form
might be
more
equal.
compact, rounder drops on surfaces for which more strongly resist penetration by small. I mean, maybe it's going to be equal because I see nothing different from that and then the other thing that we had.
Yeah.
Nice. Okay, good. Okay, so liquid X is lower, so pour it in a funnel the time it takes to pour each liquid through the funnel. So X has a lower viscosity, so it's going to take less time. So Tx will be less than Ty. And then this thing. Oh yeah, this is okay. So the thing that has the the thing that has a lower vapor pressure will have a lower partial pressure as well. So Px will be less than Py.
I see. Less than Py. Mm-hmm.
Okay, now A, lower viscosity, lower surface tension. Wax-coated particles carefully put onto the surface of A or B will stay on the surface if the particles are small enough. The heaviest mass of particle A and B that will stay on each liquid surface without sinking are measured. Okay. Now, greater surface tension means that it's inversely proportional to the size of the droplets, which means that surface tension is resistance to penetration of a surface. Fluids that form more compact drops on surfaces or which more strongly resist penetration by small objects have a high surface tension. So it's something with surface area. I don't see anything dealing with mass here. So heaviest mass of particle mass A and mass B that will stay on each liquid surface. It doesn't really tell us anything about surface area. I'm not sure about that one. The second one is talking about, that's just a viscosity thing. So the time A will be less than time B.
Okay.
Yeah, and then let's see. The heaviest mass of particle MA. Oh, wait. That will stay on each liquid surface without sinking or measured. Okay, so wax-coated particles put on the surface of liquid A or liquid B will stay on the surface if the particles are small enough. The heaviest mass of particle MA or MB, are those the wax-coated ones? All right, that will stay on each liquid. Okay, so I'm gonna guess if it's a higher surface tension, it should be, I mean, I don't know if it's just surface area or if mass comes into play here. Let me see if I can check. Surface, tension, mass. All right. Like, it has to, yeah, the weight, so if it should be a combination of surface area and the weight of the thing. That's just, okay, so basically, so A has a lower surface tension, so the mass, it should be able to handle, like, less, something that's less heavy. So I'm going to guess MA is less than MB, but if it's just with surface area, it could be equal, so unsure of that.
Want to check it?
Yeah. All right, nice. Finally. Using molarity to...
Hold on. Okay, so it's quite a bit. Okay.
This crap. Okay, let's see. Here, I'll screenshot this. So, simple cubic, nothing inside. Body centered, seems like it's just in the center. Face centered, seems like those things are on the face. If you like rotate it, all those things are like on, yeah, on the faces.
Yeah, the face.
Yeah. Okay.
Okay. It's a body-centered cubic.
Yeah.
There, right?
Wait.
This one?
Well, if you rotate it, you're gonna see that seems to be like
Well, it
it's in the
doesn't
middle.
rotate.
But look at 3.
It like switches to different pictures. See?
Let's see 3.
That one's face-centered.
That's what. Oh
Yeah,
crap! We're looking for body centered. My bad. That's body centered. Yep.
That's body-centered too.
Yeah. Right. Cool. Learning streak.
Okay. Picometers.
Alright, I'll screenshot this.
Oh, okay, so we just basically have to do the Pythagorean theorem. Ready?
Let me see like the top for a sec. Distance between the blue and the red and blue balls. Oh, okay. All right, cool. Distance between the red and blue balls is 420. Calculate the distance between the red and green ones. Okay, so that over there is... So, okay, let me draw this crap.
Well, it forms the right triangle if you did it all together.
Yeah, that's the hypotenuse of this right triangle. And then one of the lengths is going to be the answer. And then the other one is a diagonal of the... You know, yeah. So okay. So basically, let's see. Red and green balls. Okay, so red and green balls squared plus the diagonal. I'll just say red and gray squared is equal to the red and blue ball distance, which is 420 picometers. Now, the distance between the red and gray ball, like that diagonal that's on the bottom face, is going to be basically, okay, so red and gray diagonal is equal to, so that squared is equal to red green squared plus red green squared. So that is really just essentially x squared plus x squared, which is 2x squared. So that's okay, so red, gray, squared. Let's see, and then I take the square root of both sides. Hold on. X. That should be x radical 2. X rad 2. Okay, so x rad 2. X rad 2. How can I relate this? X rad 2. Oh yeah, so this can just be, okay, RG times radical 2. Okay, let me, whoops. Calculator. Start off with 420 square root. So that is 20 point... Wait. Sorry, my bad. 420 is the actual distance. So 420 squared x round 2. Shit. Okay, x squared plus 2x squared is equal to 420 squared. This is 3x squared is equal to 420 squared. Now, square root both sides. We get x radical 3 is equal to 420. X divided by radical 3, that's like 420 divided by like 1.7. 247.06. 247.06. Okay. I think that might be it.
One answer again?
247.06, or whatever the right significant digits are, I guess. So
What's the picometers, right?
Okay, let's see. X radical 2 X radical 2 here, and then this is just x. It should be x squared plus 2x squared, damn it, is equal to 420 squared. What the foo? Okay. Okay, try 240. 242.487. Does that turn into 243?
I think 242 will be it.
Okay.
Yeah.
Got it. Okay. Distance between the red and blue balls is 474. Calculate the distance between the red and green balls. Okay, this is like the same kind of thing. So 474 squared is equal to 2x squared plus x squared, 3x squared. Okay, so 474 squared divided by 3, and then square root of that, 274. Try that.
Wait, how'd you do the math again for that?
Oh yeah, so basically, so red ball to the blue ball is the hypotenuse of a triangle, where one of the sides of the triangle is the distance between the blue ball and then that gray ball that's underneath it, which is essentially just the same thing as a side length of the cube. And then the distance between the red, so here, let's see if I can. Okay, so show me with your cursor go from like, so the red ball to the green ball. The red ball to the blue ball. Yeah, so it's that one is the hypotenuse, right? And then the blue ball down to that gray ball, that is one side of the triangle. And then that gray ball to the red ball, that's the other side. That's the other side of the triangle. Now, the blue ball to that gray ball is equal to just the side length of the cube, right? And the gray ball to the red ball is basically the the diagonal of that face, that bottom face.
Okay.
All right. So if I say that a side length is x, right? Like for instance, the blue ball to that gray ball is a side length, and that's one of the sides of the triangle. So I say that that's x. And for the diagonal, that's going to be x radical 2.
Okay.
Because x is one side, and it's the other side, and then the hypotenuse is going to be, x squared plus x squared, which is 2x squared. And that turns into, when you take the square root of that, that's x times radical 2. Yeah.
Okay.
So basically, so the hypotenuse, aka red to blue ball, is 474. So I square that, and I set it equal to the side length squared using Pythagorean theorem. So x squared plus 2x squared. So that gives me 474 squared is equal to 3x squared. And then I divide both sides by 3. And then I take the square root, and then I get x.
Okay. So 274 picometers?
Yeah, I hope so. Nice. All right, now this is a little different. So now they're showing us the 2x squared value. Because they're saying between the green ball... Wait. No. They're giving us the x value now.
Blue ball.
Yeah, the distance between the red and green ball, so that's just the side length of the cube, right? So that's just x. All right? And then I'm going to add to that distance between the green ball and the blue ball. And you see how that is a diagonal for that face. So that's going to be the 2x squared. And then that's going to be equal to whatever the distance between the red and blue ball, which is that hypotenuse. So I'll put like c squared, I guess. Now, so they give us x essentially, which is 0.29 nanometers. So I'm going to do 0.29 squared plus 2 times 0.29 squared is equal to c squared. So 0.29 squared plus, let's see, parentheses 2 times another parentheses 0.29 squared, close parentheses. So that gives me Oh wait, I forgot to. Damn it. Okay, hold on one sec. 0.29. Whoops. 0.29 squared times 2 plus 0.29 squared. So that gives me 0.0841. And then take the square root of that. 0.29. What the hell am I doing here? One sec. Wait, why did I do the square root of that? All right, hold on. I'm putting it into this like computer calculator, which is not that good with the formatting. So let's see. 0.29 squared is, I'm just going to write it down on my notebook, 0.0841. And then times 2 gives me 0.1682. Add that to 0.0841. I get 0.2523. Square root of that, 0.5. That should be your answer. Yeah, and then the unit, I think, is nanometers.
Yes.
Yeah. Oh, okay. Wait, I get 0.50. Nice. What the hell? Key fact about unit cells to keep in mind is that you must be able to create the entire crystal lattice just by joining one unit cell onto another, like building blocks. What the hell is this crap? Draw a unit cell.
Oh. Okay. Okay. This seems pretty straightforward.
All right, I don't really get it, but you can take the lead.
So Heliagon? Okay, I need the explanation again.
Yeah.
It's a little stupid.
Let's see. Drag the slider to see out an entire. Okay.
Oh, here we go. Yeah.
Huh?
Oh.
Okay, so I guess we need like a 4 thing.
Yeah.
Right? Okay.
I see. Ready?
Let me do like a screenshot. Scroll like a little up, just so we have this. Okay. Yeah. Perfect. Okay. Okay, so it seems like would it
Well,
just
okay. So I think I'm getting it now.
Okay.
So you see how like when I do this, right, like on a corner, it has a shade. So, like if I go in another corner, go over here, it doesn't have a shade.
Okay. You want it to
It can't
have
be
like that
connected.
shade thing?
You want it to have a shade thing,
Okay.
and basically once you find it, you can. It's basically like Battleship. Like once you know where one pair is, you already know where the rest of it is.
Okay.
So let's see. Let's see, that doesn't work.
Maybe try the one to the left of it. Okay, and then that one.
No.
Maybe start with like the ones that are just the pink things and nothing in the middle.
Yeah, I guess, right?
Yeah. Or like the top of that. Okay. That's giving us a little bit. Can you do that with the blue circles? Okay, okay, okay.
Okay, so we know that now.
So it's on the right side of those, and then see if there's like a thing on the left side.
Let's see. Okay, so it seems like the beginning of every box of some sort doesn't have anything. Um,
Oh, I know. I think I got it. So, do the thing. So like in between, go to left.
okay.
Yeah, underneath that. Yeah, show me that. It should be like completely to the right. Like, see if you can do that. Yeah, and then above that. Oh, like in the same one, but above that, it should be completely to the right. Okay. That one shouldn't be. Yeah, and then this should be completely to the right, or it'll just be okay. Okay, there we go.
Okay.
Yeah, do above that, the pink one above that. Yeah. Above that too, and then above that, and then to the right of that. Yeah, let's like unveil like all this crap. Like do the blue ones too. Oh yeah, just in that area that we're doing. Like do the because that should be a complete. The blue one should be complete. Yeah. Yeah, this is good.
All right, so all the red balls have it.
Yeah, do that blue one all the way on the left. Like above that, the one that you have like almost. Yeah. Okay, so since
There it
that's
is.
on all sides, it should be.
All sides over here are filled.
Wait. Okay, so start with that thing on the left. That is giving us the best clue, and then just unveil like all the pink ones. Like show me like everything for the pink ones. Yeah, like that one, show me everything. Yeah, even to the left. Like do the left side of the pink ones. Yeah, like that side.
No.
Do they not let you? Okay, start with the one in the middle then. Yeah, that one. So yeah, show me everything with the pink. And then
they're all filled like this.
Then the one on the left of the solid blue.
Uh-huh.
Does it let me? Let's see if I can. All right. So. Oh, cool! I can draw stuff. So, show me this. And that, and that.
So they're all the same.
Why do they keep going to the right? Like, I want everything to... Because, like, this over here is, like, the center point, isn't it?
Let me start over. Hold on. So we want... This one's fully done.
Oh, that's just on the right? It's not the entire thing anymore?
What the?
Why was it, like...
It was literally full before, no? Am I crazy?
Yeah, it was. Try the pink ones.
Still the same thing.
Okay, everything's going to the right. So they're saying... Alright, let me look at these stupid instructions.
Let me get this. You want to work on something else? Meantime? Or you want to keep doing this? Because we can count the atoms in a unit cell.
I'm sure if we, like, look at the answer for this, it'll probably... You know what? I think it'll be... Okay, you know what? Just show me, like, do the highlight thing with as many as possible. Do it for, like, everything in here. Or wherever you want.
God, the highlighter is the most terrible thing.
It's to the right, to the right, to the right. It's always to the freaking right. And do the blues too. The blues are to the right.
Yeah, it's all to the right.
Where? Because we saw like a full blue one before. The pattern seems like there's two like empty pink ones, and then there's like the one with the blue in the middle. two-dimensional lattice. Oh, okay. Oh, and then this one too. So that should be the center. That should be the center. Oh, you know what? I think I kind of understand. We don't have to do like the entire part. You can just do it so try, okay, I think, yeah, something like that. And then this part over here and that part. Oh, it doesn't turn red?
No.
Okay, this one turns into a full circle. Alright, let's see what the explanation is for this crap.
Hold on, let me see something.
Yeah, no shit.
Oh, can you erase that?
Oh, yeah.
Really quick?
Alright, what do these assholes do? Let's see. Let me see what the answer is. Oh, let's see the answer.
So you don't even need to have a highlighted area.
Yeah, but I think the highlighted area will show us. Like, so on the top, try highlighting like over the answer and see what type of things that they show us. Okay, it's like this, right? Whoops. Yeah, it's like that. So go back to the top. Okay, so highlight this area. Let's see what they show us.
I can't highlight it.
Alright, but you see how it should look like that?
So why the hell does it look like this? Because we know there's no highlight on the left side.
And scroll up a little bit. Let's see, like, yeah, see that slider? Let's move the slider around to see the different types of things that we might get. So that makes sense. That makes sense. Okay, that makes sense too. Alright, and then unit cell. What's that? No, click another unit cell. Alright, let's try it one more time. Okay, so this is so I'm gonna guess it's that maybe. So see what the highlighting crap says. Oh, okay, that's pretty good. Yeah. Like, do everything in here. Okay. Try this over here. F. Yeah, do you like like, so the entire thing for the pink ones, just so we see if it's like a half one or a quarter one, like for the ones in the box that I drew.
I can't get around that whole box there.
All right, try these ones over here. And try the blue ones.
Where?
Oh, the blue ones, like within the boxes. Like that and that. Man, dude, this sucks. Alright. F this.
This is the stupidest chemistry exercise in the world.
Yeah, man.
What the hell am I learning from this? I then just was learning how to get a freaking aneurysm. Just count the atoms on the fucking cell.
What's this over here? Let me see this crap. Small part of crystal lattice. Unit cell is outlined in red. How many atoms of each type are in the unit cell? Okay. 8 for the first one.
No, it's
What
1,
the
1,
F?
and 3.
Okay, let's see. Unit cell is outlined in red. How many atoms of each type? Key fact is that atoms are portions of atom that are completely within, within the unit cell are counted. So, let's see. So, atoms on faces are split between 2 unit cells, so half. The one on edges, I'm going to screenshot this crap. The one on edges are split between 4, so each cell has 1/4 of that. Okay, and corners split between 8. Okay. And then okay, let me see the answer. Oh, I'm sorry. Sorry, the top, because the top shows like the unit cell. Okay, the black ones.
Okay, so it's 8.
Okay. The black ones, there's.
Yeah, which means it would make 1/8. And the black ones is half, so 1, 2, and then 3. And then for the blue, it's edges. That's a quarter. And then that's 1, 2, 3, 4, which makes up 1. Okay, so that makes sense.
All right.
So one in the units. Okay.
Yeah. So those
1,
are in the
2, 3,
corners. That's
4,
8.
5, 6, 7,
There's 8 of
8.
them. That should be 1.
1.
And then the black
And
ones,
then
they're in like they're on the
1,
faces.
2,
So that's 1, 2, 3, 4, 5,
3.
6. 6 times 1/2 is 3. Yeah, okay, cool. Nice.
This is completely on the edges, which is a 4th, right?
So edges are 1/4. So 1, 2, 3, 4. So that's 1. Wait, sorry. 1, 2, 3, 4, 5, 6, 7, 8.
5, 6, 7.
So 8
Yes.
divided by 4 is 2, right? And then
The black, it just has half.
Yeah, so 1, 2.
1.
Yeah. Cool. Oh yeah, now we have to name this. Top layer colored red, atom second layer colored green. Third layer colored blue, dragging the slide. Alright. Okay. So let's drag that crap.
Alright, so here's the difference between them.
Let me screenshot it.
So this one is maybe cubic, right? Yes. Okay, this is easy. This is going to be a hexagonal, right? Well, it's not close packed though, so no. This is close packed.
I think that's hexagonal close packed.
Yes.
Awesome.
Hexagonal.
Is that
again.
cubic?
No, cubic would be on the sides. It's not on top.
Okay.
What the?
Yeah, I think
Okay,
that's
so
a
maybe you
cubic
are, right?
one. Because those green atoms are like making cubes.
Oh, it was just no. It wasn't.
Oh, that's
packed.
stupid.
Oh, wait. That was on me. My fault. Yeah, I was supposed to be closer packed than that. None of the cells were touching like that.
Okay.
That's my fault. It's me going too fast. Alright, now this is cuboidal. The CCP.
Isn't that the Chinese Communist Party?
Yeah. I was hoping you would get it.
Is
this
like...
is no.
Okay.
No, this is the hexagon.
Yeah. Yeah.
Cool beans. Finding an atomic radius from an FCC or BCC. Oh, fuck.
Yeah, okay.
Okay, so it's basically the same thing, so we're just using
Yeah, let me
radius formula.
it's like scroll so you can so I can see like the explanation. Yeah, have it so the explanation is like yeah, okay, perfect. Okay. Oh yeah.
I'm back.
So are your classes returning to in person or
No, not for me.
do you think we're gonna
I'm
have another
online still.
lockdown?
No, it's impossible.
What makes you say
They
that?
won't do it. They won't do it because the
I
Delta
mean,
variant isn't making the vaccinated people sick like that.
yeah,
It's the people who are unvaccinated, so they're just trying to get people to vaccinate.
got it.
Yeah.
All right, let's do this stupid crap over here. Yeah, let's do it. Body centered, which means that the one between the two vertices is going to be okay. So the radius is that lattice constant. Lattice constant is A. Okay, so okay, 4r squared is equal to okay, so that's that one, and then this one going down 4r squared. 4r squared. It's that. Wait. All right, lattice constant A is the width of the unit cell. Okay, I got that, so that should be A squared plus 2A squared. Okay, I get 3A squared. All right, I can do this. Let's see. So we got 177 times 4 squared divided by 3 square root. I get 408.76. So that should just be 409 point, right? Picometers. Nice. All right, now the face-centered one is going to be slightly different. That's just going to be, let's see. Oh, they start off with the lattice constant, okay. All right, we got to get the radius. So 4r squared is equal to 2a squared. Let's see. This is 16r squared is equal to 2a squared. Divide 16, and then do the square root of that. So I get, okay, 532 squared times 2 divided by 16 square root. I get 188 point whatever picometers.
Body centered.
So body centered, I'm going to do the thing that I did before. So let's see. And they got, all right, we have A. So this is going to be 372 squared. Whoops, I hit cubed. 372 squared times 3 is equal to this. Oh, yeah, and then divided by 16, and then square root of that. It should be 161, like, point, you know, and then picometers. Yep. Rank solids in order of decreasing melting point. Okay. Okay, so like scroll, so the explanation is on top. I'm gonna take a screenshot. Yeah, you can go down a little bit more. Yeah. All right.
Molecular, right?
Yep. Wait, no. Fe is going to be atomic.
And why is that?
And just because it's just it's going to make, like, it's just iron. So like the type of solid is just going to be iron attached to iron and stuff.
Oh, okay.
The CH2Cl3 though should be molecular.
Yes, I just realized that.
Yeah. So this is
It'll
going to be
dispersion.
I mean, it's going to, I guess.
Metallic bonding?
Oh, wait, one sec. Okay, dispersion. Okay, yeah, metallic. Then I think this will be like dipole.
Yeah. Let's see. See, it's the first one, so I always try and gauge.
F my life. Okay, let's see. Oh wait, no, sorry, wait. CH2Cl3.
Cl2. I don't know if that'd make a difference. But...
CH2Cl3. What the hell? You know what? Sorry, neon should be atomic, I think. Yeah.
Yeah.
Okay.
That's what I put at first.
Yeah, I should have.
HBr.
Ionic.
Krypton should be atomic, right? For following what neon.
Wait. HBr is molecular. I mean, yeah, molecular.
Oh, yes. Sorry. And FEI, that's going to be ionic.
Yep.
Metal. Non-metal. Force holding it together. Oh, for atomic, it's going to just be a dispersion force. HBr should be... It's not hydrogen. Like, no, not ionic. It should be covalent, no?
Oh, wait.
Or dipole. Sorry.
Maybe, wait. It says intramolecular forces weak. But not dispersion. Intramolecular forces. HBr solid. What? Okay, so HBr. Maybe dipole?
That's what I was thinking.
Yeah, let's go for it.
And the FEI is going to be a metallic, an ionic bonding.
Yeah.
That's going to be the highest because it has a metal in it. This will be the second. This is lower.
Nice.
Let's see. Manganese is a transition metal.
Yeah. It'll just be atomic.
Atomic.
Metallic
Force
bonding.
holding it together is metallic, and it'll have the highest since the rest of this.
Highest, you mean?
Oh, whoops. Yes. I just said highest and I put lowest. H2O. This
N2
is hydrogen.
gas
This is going to be...
N2 gas is molecular. Dispersion
covalent?
and lowest.
Or dispersion?
And then H2O is going to have hydrogen bonding.
And then
H2O, yeah, molecular, right? Yep. All right.
Finding density.
Oh, Jesus. Okay, so let me screenshot this crap.
God damn it. Which ones we don't want to do are the only options now. Where has that lich? Back to me. Where did I leave you? Back to me.
Okay.
What?
Nothing. All right. All right. Let's just let's go for it. FCC, Lattice Constant. Okay, so the formula seems to be, let's see. Okay, so density is equal to N is the number of atoms in the unit cell. M is the mass of each atom divided by A cubed. So, okay, they give us density, so that's going to be 2.7 is equal to, all right, might as well just multiply it by A cubed. So 0.405 cubed is equal to, there's going to be 4. So divided by 4, and we got to find, wait, and then M is the mass. So that's going to give me the mass, and then we're going to find, using the mass, we're going to find the identity of it. So I'm going to do 0.405 cubed times 2.7 divided by 4. Oh crap, wait. Oh, M is like, okay, wait. M is equal to the mass of the molar mass over Avogadro's number. So, damn it. Molar mass. Because it's the mass of each atom. Okay. So, atomic mass divided by Avogadro. Okay, so since Avogadro's number has that exponent, do you have your calculator nearby?
Mm-hmm.
Okay. So do this. So multiply. Okay, so 0.0448. Multiply that by Avogadro's number.
.2697856. Because it's 6.022, right?
Yeah, times 10 to the 23rd.
Yeah. I omit that in this.
So what's so it's what you just told me times 10 to the 23rd power?
Yeah.
What the hell? Oh, damn it, I have to convert the units. Okay. Alright, so let's see. Nanometers. Okay, so 0.405 nanometers times 10 to the negative 9. Centimeters, negative 2. So, negative 7. Okay.
What'd you say?
I was just converting, so it was 0.405 nanometers. 1e neg 9 nanometers in 1 meter. 1 meter is 1e neg 2 centimeters. So this divided by this is negative 2 minus negative 9, which is 9 minus 2, which is times 10 to the 7th power. Okay, so positive 7. Positive 7, okay. Cube that. Let's see. So 0.405 cubed is 0.0664 e. 7 cubed multiplied by 3, 21. Okay. Times 2.7 divided by 4. So 0.0448 E21 is equal to M. And now multiply that by Avogadro's number. So this times 6.022 is 0.27. Hold on. Wait. Shit. No, it'll be negative. Sorry. Negative. E2. So 27. See in the periodic table what, wait, 27, that's too easy. See if there's any element that has, 27, aluminum or silicon. I don't even know if that makes sense here. 27. I wonder if we get it if we just look for the density. 2.7.
Want to try it?
Well, you could see in the period.
Right.
All right, cool. But let go to the periodic table for a sec. I just want to see. like for aluminum, it says density. Here, like scroll down so you can see that what the density is. So we could have just used the density function. All right, cool. Now let's see. This is a type of sodium. A is that. What's the density? Okay. So this is going to be 4 times M. Okay. Sodium's molecular weight. What's that? Molecular weight of sodium.
Sodium molecular weight.
23. Okay. 23 over 6.022. Okay, 23 divided by 6.022. 3.82 E negative 23. Okay. Okay, times 4. So this is 15.3 E negative 23 divided by A is in picometers. That's times 10 to the negative 12, right? Yeah.
I'm sorry?
So 525 E neg 12.
Pico is 10 to the negative 12.
Yeah, and then centimeters is times 10 to the negative 2. So this is times 10 to the negative 10. 525 times 10 to the negative 10 cubed. So times 10 to the negative 30. 525 cubed. 525 cubed. Geez, that's a huge ass number. Alright, whatever. Jesus. Alright, wait. 1, 2, 3, 4, 5, 6, 7, 8. So this is 1.4 E negative 22. Okay. Alright. And then 15.3 divided by what did I write there? 1.4. 1.4. So this is 10.9 E, so the negative 23 minus negative 22 is just 1. Uh, 109? What? Yeah, let's look at the density of sodium. Let's just get like an idea.
Density of sodium is like 980 something. 968, there we go.
Wait, yeah, that's in, okay.
0.9.
Wait, 0.968? 0.9,
Well, it's just asking for the number in this one. What'd you get, 106?
Yeah, I got something too big. Let me check my math over here. 1.4 E negative 22 goes into that. Neg 23 minus negative 22 is 22 minus 23. Oh, negative 1. So maybe it's 1.09. that could be it. That seems to make more sense. So 1.09 or whatever. Okay, what did I do here? Face-centered. Lattice constant. Here, I'm gonna write some stuff down and put it into your calculator. Let's see if that helps. So, basically, density is okay. So we're gonna start with m is equal to molar mass divided by Avogadro's number. So m is equal to, so the molar mass of sodium is 23 divided by 6.022 e negative 23. So what do you get for that?
Say that one more time.
Oh, I wrote it down. Can you see it? Oh, I have to do that. Sorry. You see it?
Oh, there you go. So 23. 3.81.
.81 e negative 23. Okay, that's what I got too. All right, next will be. Okay, so 525. Okay, 525 e negative 10 yeah, so cube this over here.
About the cube root. I got it. 8.06.
Wait, when you cubed 525 times 10 to the negative 10 power?
So negative 10 power?
Yeah, see what I wrote? 525 times 10 to the negative 10 power.
Sorry.
Yeah, when you cube that, what do you get?
It gives me a syntax error. Oh wait, I'm dumb.
Put it in the
Hold
parentheses, yeah.
Still same thing. Except it's the negative 4.
All right, okay, then just do 525. All right, here, I'll do it.
What, cube root?
No, here. 525 times 10 to the, damn it. Okay, that times 525 is this, and then cubed is that, how can I have this in a? All right, this is all right. 1.4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, that's what I got before. 1.4 E negative 22. That's annoying. Okay. So, where's the annotate? Alright, then, so that's equal to 1.4 E negative 22. Alright, so then we do 4 times 3.81 E negative 23 divided by 1.4 E negative 22. Parentheses didn't show up, but so 4 times 3.81, 15.24 times 10 to the negative 23 divided by 1.4 E negative 22. So this divided by 1.4, get that, and then negative 23 divided by negative, so minus negative 22.
10.88.
Yeah. And then since it's times 10 to the negative 23 subtracted by negative 22, it's 22 minus 23, which is negative 1. So 1.088. I still get the same one.
Hmm. It's 1.06.
Oh god.
Oh man.
They suck.
Well, anyway, man. It is like basically the end of our time here. There's definitely way more to go over this. But it did good. We started at 35 and getting 3. That's good. You see they have a knowledge check after the lessons?
Mm-hmm.
Like certain lessons are complete, so the 38 can like jump.
Okay.
Because it'll start like quizzing us on the new material that'll start coming up.
Yeah.
And whatever, and if we like pass most of it, they may like shoot us up like 10%.
Mm-hmm.
So.
Okay. Oh wait, are we out of time? You're saying?
Yeah.
Okay.
Yeah. So.
All right. So next week, right?
Yeah, next week.
All right.
Yeah, next week on Wednesday. That's good.
Okay.
For me.